Hi students, today we are going to discuss one application in surface tension. The topic is excess of pressure. Now let us assume that water is taken inside a test tube or in any narrow tube. If you pour water and look at the top surface of the liquid, you can see it will be concave if it is water. And we call that there are two meniscus. One is upper meniscus, which is circular, is it not? The lower meniscus will be curved. So from the top, when you look at the liquid, it appears like a bowl which is concave shape from the top surface when you view. And now there is a force due to surface tension at all the points of contact of the liquid with the solid tube. The force due to surface tension will be tangentially acting like this in all the directions. And when you resolve this tangential force into two components, okay, upward it is t cos theta and horizontally it is t sin theta. Now all the t sin theta components are horizontal, they are equal and opposite, they cancel each other. Now all the t cos theta components are perpendicular to the surface of the liquid and they are tangential to the outer circumference of the top layer. And cos theta, theta is equal to 0 for pure water. So let us assume cos theta is cos 0 is equal to 1. Therefore the net force due to surface tension is T itself. So now you can see that at each and every point on the top surface, the force due to surface tension is T. So what is the net force, net resultant force due to surface tension in the upward direction? That must be equal to Ft. That is, we have to multiply T into the circumference of the circle. Okay? Okay, suppose if this resultant force is acting in the upward direction, then what should have happened actually to the liquid? It should have risen upward and overflown out of the tube. Is it not? But that is not happening. The liquid is at rest. That means some other force is acting in the downward direction which is compensating the force due to surface tension. Yes. What is that force? That force only is due to the pressure difference between the liquid surface or inside the liquid and outside the liquid surface. So now children, a force due to pressure difference is created. We have already studied that the pressure on the concave side will be greater than the convex. Is it not? So now this is convex surface and the top is concave. So the pressure outside should be greater than the pressure inside, so that the pressure difference should create a force in the downward direction. The force due to surface tension is upwards. To compensate this and keep the liquid in equilibrium, another force is created due to the pressure difference between the liquid surface and the vapor side. Okay, so that is denoted by delta P, change in pressure. That is P1 minus P2 or P2 minus P1 as you give the symbol. Okay, so this is the concept you have studied. Now, these two should be equal. When the liquid is said to be at rest or in equilibrium, the force due to surface tension Ft must be equal to the force due to the pressure difference Fp. This is the concept we are going to apply in all the derivations. Moreover, we have studied pressure is defined as what? Force per unit area. Is it not? You see, change in pressure must be equal to force due to pressure divided by area. Therefore, force due to pressure must be equal to change in pressure into area. Area of a circle is pi r square, where r is the radius of the sphere. So, this is the equation we are going to apply in the following derivations. Okay, are you ready now? So, let us derive an expression for the excess of pressure inside a liquid drop first. Now, let us assume a drop of a liquid, just like a raindrop. So, raindrop is spherical in shape. This is due to the surface tension of the liquid, water. Okay, what is present inside a raindrop? Fully it is occupied by water molecules. There is no hollow space inside. Is it not? So this is assumed to be a raindrop. So inside a raindrop it is fully occupied or filled with the liquid molecules. There is no space inside. Therefore, only one outer surface it will have. So how many free surfaces are there in a liquid drop means it has only one free surface. Okay, that is the outer surface. Yeah, let us imagine now it is cut into two halves. Okay, so one half drop I have taken, it is fully filled with the liquid inside, no hollow space. So now the force due to surface tension is going to act all along the outer surface, tangential to the outer surface, it is going to act like this. And the net force due to surface tension in this picture is shown towards the right side, So Ft is the force due to surface tension which is going to act towards the positive x-axis. To compensate this force, a pressure difference is created and the force due to pressure difference must act towards the left side. Okay, so this is the direction of the force due to pressure difference. And also we have studied that in the concave side only the pressure P2 will be greater. On the convex surface side the pressure P1 will be always lesser. Who is present on the left side of the liquid is the vapor, air, vapor pressure. So vapor pressure is lesser, liquid pressure is greater. So the pressure difference must be P2 minus P1. Okay. So now we write the expression for the force due to surface tension. Force due to surface tension, it is acting all along the circumference. Therefore, Ft must be equal to what? 2 pi r multiplied by T. This is equation 1. So, what should be the expression for Fp? What is Fp? It is a force created due to the pressure difference across the liquid surface. And that must be equal to the change in pressure P2 minus P1, higher minus lower pressure, into area, the area of this circle, that is pi r square. So delta P into pi r square, this is equation 2. Already we have discussed that Ft must be equal to what? Fp, or Fp must be equal to Ft. Substituting 1 and 2, now delta P into pi r square, delta P into pi r square must be equal to 2 pi r into T. So from this we get delta P, the change in pressure across the liquid surface is equal to 2T by R. This is the third and the final equation. Have you understood this? Okay. Now pressure inside a liquid drop. I told you that if it is a liquid drop like a raindrop means it is fully filled inside with the liquid so that it is having only one free outer surface. Imagine in the water cans, water bottles or a bubble can where the inverted water bottle is kept. Sometimes when you open the tap, a bubble will come from the bottom. Is it not inside the swimming pool and all? Air bubble. It is spherical in shape, and what is present inside an air bubble? Fully air molecules. There is no liquid there. So there also it is fully filled with air. Air bubble also is having only one free outer surface. Is it not that? So for air bubble also, what is the pressure difference equal to? 2T by R. The same derivation only in the exam. If they ask to derive an expression for the excess of pressure across the liquid surface or across the liquid drop or air bubble, both are one and the same. That is delta P equal to 2T by R only. Now let us take a case of excess pressure inside a soap bubble. Now let us take a straw, dip inside a soap solution and blow some air. As you inflate it, it expands in size and you can see a colorful spherical bubble. Is it not that? That is called the soap bubble. As you blow air into it, inside the soap bubble only air gets filled and there is no soap or soap solution inside. No material other than air. Is it not that? Where is the soap solution present? Only on the surface, outer surface, which is hollow. This sphere is hollow. This sphere is hollow. So inside there is no soap, but there are two surfaces. One is the inner surface, other one is the outer surface. So here force due to surface tension is going to act on both the surfaces. So here you can see that blue color arrow marks. These blue color arrow marks. These are all the force due to surface tension acting on the outer sphere, tangential to the outer sphere. And these red color arrow marks. These are all tangential to the inner surface. Okay. So in this case, since there are two free surfaces, respectively the outer surface and the inner surface, the total force due to surface tension must be 2 into 2 pi r into t. For one surface we wrote 2 pi r into t here. Therefore for two surfaces it must be 2 times 2 pi r into t. So Ft must be equal to what? 4 pi r into t. Okay, this is the only additional point than the previous case. So Ft is equal to 4 pi r into t is the equation 4. Now also there is a pressure difference which is going to compensate the force due to surface tension. So P2 must be greater than P1. Liquid pressure must be greater than the vapor pressure. Therefore P2 minus P1 is delta P. So the force due to the change in pressure must be equal to P2 minus P1 into pi r square, or delta P into pi r square. This is equation 5. Here also for equilibrium, at equilibrium, Fp must be equal to Ft. So when I substitute delta P into pi r square, that is equal to 4 pi r into t. So reducing it, we get delta P equal to 4t by r. It is twice the previous case. So in the case of liquid drop and air bubble, we have got delta P equal to 2t by r because it is having one free surface. In the case of a soap bubble, we are getting delta P equal to 4t by r, that is 2 into 2t by r. This is because the soap bubble has two free surfaces. This is the only difference. Okay, let it be whether it is one free surface or two free surfaces, the delta P must be inversely proportional to r in both the cases. Is it not? What does this mean? When the radius of the sphere is small, excess of pressure will be large. When the radius of the sphere is large, then the excess of pressure will be small. Is it? Now in our everyday experience, while blowing a spherical balloon, when you pump air into it, first initial blowing is very difficult. Then after it is acquiring a large shape, blowing is easier. This is the reason. So reason type question also they may ask, why is it difficult to inflate the balloon earlier, initially, and then it is easier when its shape becomes large. This is because the change in pressure is inversely proportional to the radius of the sphere. Okay. So my dear students, you have to remember that the excess pressure inside a liquid drop as well as air bubble will be the same derivation, and the expression is delta P equal to 2t by r for one free surface, and the excess pressure inside a soap bubble is delta P equal to 4t by r because it is having two free surfaces. I hope you must have understood well. Fine.